recording now, so Norman, try to contain yourself. All right. I'm going to pop this into slideshow mode. There we are. Okay. What I've got here is kind of the next step. We're talking about Kirchoff's laws, and the first one was you go around any loop, and the sum of all the potential drops and gains, adds and losses, should add up to 0. And it's basically the law of conservation of energy. It's basically saying the energy we put in equals the energy we get out. The second law is Kirchoff's junction rule. It says that the sum of the currents entering a junction must be equal to the sum of the currents leaving that junction. So on the face of it, you'd say, man, that just kind of makes sense, Mr. Everly, because if I've got little electron dudes, or whatever the charge carriers are, whatever you believe they are, thank you, Ben Franklin, if they enter this junction, they're not going to like take up residence there. They're not going to disappear from the face of the earth. However much charge goes into this junction, it's got to come out of this junction. Okay? My honors students have a hard time sometimes with this because they confuse voltage with current. Okay? Think of voltage as the energy. Now, it isn't directly the energy, right? It's energy per unit charge, but for the moment, think of it as energy. Voltage is how much energy the battery is putting in and how much energy the resistors are taking out. Current is totally different. Current is kind of like cars on the highway. If 20 cars come out of the garage and start heading down the highway and they reach a turn, some are going to go straight and some of them are going to turn right. The total number of cars going straight and the total number of cars turning right have to add up to what you started with, assuming no accidents, no breakdowns, because that doesn't happen to electrons, right? They won't crash into something and get stuck. You're going to have the same amount. So make sure there's a strict division in your head between current and potential difference. That's huge. Once you get that, these problems aren't so terrible. All right, so the junction rule kind of makes some sense. All right, now that means that there's a very simple equation here. Anything entering a junction we'll call positive. Anything leaving a junction is takeaway, is negative. So for this particular junction, we'd say I1 minus I2 minus I3 equals 0. Or a more common sense approach might be to say that I1 equals I2 plus I3. But quite often we write it this way because later on we'll end up with a system of equations. And if they all say equals 0 at the end, it makes the system a little nicer to solve sometimes. Okay, yesterday we did the 2 battery problem. Did we talk about adding resistors in parallel? So one thing that we learned last year, that just as a review, remember if they're in series, there we go. Yes. Okay, I think that little sound means my pen has disconnected from the system, so hang on just a second. Oh, little green light comes on. I may have to edit this out. Yay! Okay, so yesterday we said, oh, just add them up. Remember from last year, this is series, that if we're in parallel, we have to flip and add them and then flip the answer. also recall that this is the exact opposite of capacitors. With capacitors, if they're in series, we flip them all, add them, flip the answer. If they're in parallel, we just add them up like normal numbers. Resistors, exact opposite. If they're in series, add them up. If they're in parallel, flip, add, flip. Okay. So, let's do a couple of examples, and I'll stop talking at you. We'll keep it nice and simple today. All right, so this example, we've got a battery with an EMF of 20 volts, an internal resistance of 1 ohm, and then we've got a network of resistors, kind of a series parallel combination going on here. And it says, find the potential difference across the terminals of the battery. Oh boy. Okay. I need a little bit of room to do this if I'm going to do this on the whiteboard, on the magic whiteboard. There we go. So let's see if I can fit it all in. I made the diagram a little too big. So I need the potential difference across the battery. And we know how to do that because we did it yesterday. We're going to start here, and we're going to take the potential drop here on the little resistor and add on the effect of the battery and figure out, okay, if I put my voltmeter across this battery, what's the total potential drop or total potential gain going to be? What's the potential difference, in other words? But what do I need in order to do that I don't have? The current. Yeah. So remember what we did. See if I can change color here. Come on. See if it works. The direction of flow, the EMF or the EMF arrow points that way. So if I go from B to A, I'm going to say E minus IR. You say, oh, drat, I don't know I. So we got to get the current that's passing through the battery. How are we going to do that? Yeah, let's add the resistors. One way to do it is add up this network of resistors and figure it out. So, switch to black. Okay. Where are we going to start adding? Let's do the two in parallel first. I've got 4 ohms here, and I've got 12 ohms here. So I'd like to turn this into one big resistor. So my circuit's going to look like this. Battery, resistor, resistor, okay? And I'd say, okay, this dude right here, my combined resistor, call him resistor 2,3. It's going to be 1 over 4 plus 1 over 6. Then flip. Now find the common denominator there. I'm sorry, it's 12. Sheesh, I am totally awake today. My apologies. I'm getting better at this. There we go. Yeah, so a common denominator obviously would be 12. So I'm going to have 3 12ths plus 1 12. That's 4 12ths. Take 4 12ths and flip it, and you get 3. So that tells me that R23 equals 3 ohms. All right, R1, 6 ohms. That's where I got the 6 from. and internal resistance is 1 ohm. Okay, so what's the relationship between those three guys? They are definitely in series. I know they're in series because as current comes out of the battery, it has no choice but to pass through all three. There's no turn-offs. So if they all have the same current, they must be in series. So that means I've got like 10 ohms of resistance total. So I can really go simple and say it's a 10 ohm circuit sitting on a 20 volt battery. Oh man, even made the math nice, right? So if I equals V over R, or if you want to say E over R, for EMF over R, we've got 20 volts over 10 ohms. So there's a current of 2 amps passing through the battery. So now we can answer part A, the potential difference across the terminals of the battery. I'm going to start at B, actually, and say, all right, I've got E minus IR. All right, if you want to include VB and VA, be my pest, but what we're going to end up with is E minus IR equals VA minus VB, which is that potential difference we're after. So, again, didn't leave myself too much room, but it's going to be 20 volts minus I. I is 2 amps. Times R, which is 1 ohm. So 18 volts is the potential difference across the battery. So that's a little extreme, but what we're saying is if we take that battery right out of the package and put our voltmeter across it, it reads 20 volts. If we connect it to this circuit, it'll suddenly read 18 volts because there's internal resistance. So like I said, that's a little extreme because in real life there wouldn't be quite that much drop, but there is a drop. So we are more realistic than the perfect circuits we had last year. Find the power dissipated by each resistor. Okay, power dissipation is I squared times R. So it's very easy to find the power dissipation for this guy and this guy. Because you imagine current coming out of the battery, it's got to be the same as the current going through R1. Is that really obvious or not? Okay. What's a little different here, though, is that when we hit this junction, some's going to go that way, and some of it's going to go that way. So when we do an I squared R on those dudes, we don't know I, because we don't know how much current is going through each branch. Now there's a couple ways to figure it out. Because the numbers are so nice, that is, the resistance of this guy is 1/3 of the resistance of this guy, we could guess what the current is going to be, right? More than guess. If he's got more resistance, is he going to have more or less current? Less. Yeah. So 2 amps, I bet 2/3 of it's going this way and 1/3 of it's going this way. But, let's go ahead and play the game, though. Go back to this circuit here and take a look at that resistor. Okay. Before I do that, let me ask this question. What do I know about the voltage of those two guys? It's got to be the same. And it will be the same as the voltage across my imaginary 3 ohm resistor when I put them together. How much current is going through my imaginary 3 ohm resistor over here? I know it's 2 amps of current, right? So V equals IR tells me that this has got to be 6 volts. That tells me this guy is 6 volts, and this guy is 6 volts. Now we can use that to figure out the current, we can change our power equation, because remember, P is I times V. Since I is V over R, I can say that the power equation is V squared over R. So it's actually enough that we know the voltage. We can stop there and now stick that into our power equation to figure out the power dissipated by each of those guys. So we know the top one is 6 volts, 4 ohms. The bottom one is 6 volts, 12 ohms, and we can do a quick power dissipation. And notice the power dissipation of the bottom resistor, R3, has got to be less. Makes sense. There's less current traveling through him. Okay, so A and B, not too bad. Just did this example to illustrate some things about how these circuits work. Okay, so will I see all of you second hour? Okay, we'll come in and we'll do a couple of problems. I don't intend today to be a very strenuous day at all, and we'll take it from there.